Hello class, it's time for dynamic fluids. So remember our fluid behavior. They break down into two separate categories, static fluids and dynamic fluids, which we're going to talk about today. Remember, static fluids has to do with the pressure as you go deeper into the fluid. P equals P naught plus rho GH or delta H. Remember Pascal's principle, that when you apply a pressure to a static fluid anywhere, it's distributed undiminished everywhere through the fluid. And remember buoyancy force. Those are the big three things in static fluids. In dynamic fluids, we're only going to talk about two things because dynamic fluids are actually quite complicated. So, basics of moving fluids. Since it is quite complicated, we're going to make a simplified model, what's called an ideal fluid. So we're going to assume four things, essentially. We're going to assume that the fluid has a uniform density. This is great for liquids. It's not so great for gases. Gases tend to compress when they're moving fast in particular. We're going to assume that the fluid is irrotational. That means no spinning or vortices. So like you see here how you get a nice smooth flow over the top of this car in the wind tunnel. That's what we're talking about. We're going to assume we have a steady flow, no time fluctuations. So we don't want any time dependencies. And last thing, no internal friction, so a non-viscous fluid. This means that something like syrup, sludgy kind of things like tar. Technically, tar is a fluid. When you get it hot, it flows. But we don't want anything like that because that will introduce complications that we're not prepared to deal with without calculus. So, if all these are true, then we have a special kind of fluid that's called a laminar flow fluid. Now, laminar flow has what's called stream tubes. So here's a glacier. This is a classic example of laminar flow. Take a look. See how they're nice, smooth. Everything stays in its lane. So like the stuff over here doesn't mix with the stuff in here, which doesn't mix with the stuff in here. So it's as if there's walls between the moving lines, like lines on a road and you can't change lanes. That's what laminar flow is like. Turbulent flow, on the other hand, is when you get mixture between the tubes, the stream tubes. So here is laminar flow on the left, turbulent flow on the right, where it's all mixed up, it's all churning. So we're not going to talk about this, that's too complicated. We're going to talk about the basics of laminar flow. Here's another example from my past as an aerospace engineer. Is you see the nice smooth stream tubes. So none of the air in this tube mixes with the air in that tube, and it doesn't mix with any of the tube air down here. Until we get to the end, it gets a little bit messed up. But this is a classic example of turbulent flow, where you can see the tubes starting to mix up inside here, and you see it churning around. That's no good. We have laminar flow down here, we have laminar flow up top here, but it starts to get churned up in this region. All right, so stream tubes are like pipes, just like a pipe that's holding water or a hose, garden hose. In these tubes, we have conservation of mass. The mass that enters the tube must be equal to the mass exiting the tube. So the mass flow rate, mass that goes in over time, has to equal the mass that comes out over time. That's critical. It's conservation of mass. We can derive what's called the continuity equation. So if we assume the density stays the same, that's one of our assumptions in this laminar flow, then I can substitute in, remember mass equals density times volume, substitute that in, and I'll get this equation because the density will cancel out. So the volume, that's not velocity, that's not volts, that's volume, flow rate that goes in must equal the volume flow rate that comes out. The units are meters cubed per second, volume per second. If you take the volume, and remember that a volume is an area times a length, and you plug that in, then we end up with an area times a delta x over delta t, which is a velocity. So the velocity of the flow going in the tube And the area, cross-sectional area of the tube, must equal the velocity in the cross-sectional area of the tube coming out. What are the consequences of the continuity equation? So here is a flow tube that I've drawn. I have a big area here and a small area coming out. Area 1 is large, area 2 is small. So the velocity going in area 1 will be slow, and the velocity coming out, area 2, will be fast. You all know this because you've all taken a hose, a garden hose out in the yard, and you have put your thumb over the end to make it squirt out faster and go farther and hose down your friends with water. Our second main idea is applying conservation of energy to a flowing fluid. Conservation of energy applies to moving fluids, and this is the way I always write it in class for my students. The energy at the beginning plus the work done going from state 1 to state 2 equals the energy at the end. If we split this work up and put one on either side, we get the work on the front end and the work on the back end. And remember that in mechanics, our energy came in two varieties. It came in potential energy, mgy, and kinetic energy, 1F mv squared. So this is the work on the front side, and the energy on the front side equals the work on the back side plus the energy on the back side. And if we divide by the volume, we get Bernoulli's equation, which is energy per volume, which is energy density. So Bernoulli's equation is nothing more than conservation of energy divided by volume, which is the energy density of the fluid. So work divided by volume, if you do the math, it ends up being pressure and potential energy. M over V gives you density, and M over V gives you density. So you get this. It looks really ugly, but all it is the work on the front side plus the potential energy on the front side plus the kinetic energy on the front side must equal all of that on the back side. And that's Bernoulli's equation. And we apply Bernoulli's equation just exactly like we do conservation of energy. We only look at the two spots that we're interested in. We don't care what happens in between. All we're looking at is what's the state of the fluid on the front, what's the state of the fluid at the end, and we compare them. They should be equal.
Implications of conservation of energy. So here's Bernoulli's equation again. So I've drawn a flow tube here, and it's the same one I drew before for continuity. In continuity, we know that the velocity going in and the velocity coming out won't be the same if the areas are different. Smaller area, higher velocity. So for this particular flow tube, let's apply conservation of energy. So we have a pressure, a potential energy term, and a kinetic energy term on this end. We have a pressure, a potential energy term, and a kinetic energy term at point 2. Now, notice that the average height of the fluid, or the flow tube, is the same on both sides. So this potential energy term, on average, is the same because the fluid hasn't gone up or down as it's moving through the tube. So that means these two terms are the same, and I can cancel them out, which leaves me with this down here. Now look, we know from continuity that the velocity at location 2 must be larger. So that means the velocity over here is smaller. So that means the pressure on this side must be larger. So as the velocity in the fluid increases, the pressure inside the fluid must decrease. This must be true. There's a couple of reasons why we can explain it to be true. First of all, it must be true because in order for this fluid to increase in velocity, there has to be work done on this side, pushing it in more than the work on this side, pushing it back. So therefore, there must be a net work, higher pressure on this side, to speed the fluid up. Second thing is a little weirder to think about, but physically the pressure must be less on the faster fluid because for the same volume of fluid, so I have a volume of fluid over here, and I have a volume of fluid over here, there's more surface area in contact between the flow tube and the fluid in the faster moving section. Okay, so we have this fluid here, this volume, it's skinny, so it has a lot of surface area of tube around it, whereas this same volume here has only a little bit of tube holding it in place because it's really fat. We have more area over here, so the area is larger for the atomic collisions that are going on, so therefore less pressure. Over here we have less area, since there's less area on the left, location 1, for the collisions that are occurring, there's more pressure. Okay, here are some implications of Bernoulli and continuity equation. So here is an airfoil shape. This is the cross-sectional area of a wing. So notice we have stream tubes coming along. Notice the top stream tube gets scrunched. So therefore we have less area here than we have here. So therefore the velocity of the air up top is greater. Down below, the stream tube passes by without changing shape, so the velocity remains the same. So I have higher velocity, lower pressure up top, lower velocity, higher pressure area down below. That gives us a net force upward called lift. That's why a plane flies. That's why the wings are shaped this way. If you're a baseball fan, curveball. So if you spin the ball this way, and the air is flowing past it across like this, the spinning ball will pull the air past on the top, so it's faster. The spinning ball will push against the air on the bottom, so it slows down. So you have slow air, higher pressure, faster air, lower pressure up top, so you get a net force up. So this ball, thrown this way, will tend to want to curve upward. If you ever gone to a department store or something where they have a beach ball above a fan, and it just stays in this flow, Because when the beach ball tries to move outward, it's out here. It has fast-moving air over here, slow-moving air over here, so the higher pressure pushes it back into the flow. You can do this with, say, like a ping pong ball and a faucet. Tape a ping pong ball to the end of a thread, and then turn the faucet on, and then if you swing the ping pong ball over into the flowing water, it will get trapped in the flowing water, and you have to pull it out. Another example is, say, like during a hurricane, you have very high winds going over the top of a house. So you have static, high-pressure air inside the house, you have low-pressure, fast-moving air across the top of the house, and so the high pressure inside the house pushes the roof off. The roof tends to get blown off of houses when there's high wind across the top. Okay, so let's look at a question. So I have this container, it's filled with fluid, it's open to the air out top, and it's open to the atmosphere down here because I have an opening, a hole. What does the static fluid pressure tell us? So if we go back to thinking about static fluid, if it just sat there and static, then the pressure up top here is less than the pressure down at the bottom down here because there's a height of fluid above it. Now, this higher pressure is what pushes the fluid out, because out here, it's open to the atmosphere. So right here, the pressure at this opening is atmospheric, and up top, the pressure up top is atmospheric. But down here in the fluid, it's got to be greater than atmospheric. So therefore, this pressure here is greater than here, so it pushes the water out, or the fluid out. What does conservation of mass tell us? All right, so the water here is flowing down, the water here is flowing out, so it's moving. Because there's a big cross-sectional area, this is a small cross-sectional area. So the velocity coming out is much greater than the velocity of the water here moving down the container.
So what does conservation of energy tell us? Well, that's Bernoulli. The energy in the fluid at the top must be equal to the energy of the fluid coming out the hole, and so we need to apply Bernoulli's equation. So let's take a look at that. Hey everybody. Okay, so here's our picture. We have this container, fluid at the top, hole at the bottom, water flowing out. Bernoulli's equation is this. So now, first things first, the pressure at the hole and the pressure at the top of the fluid, they're both open to the atmosphere. So these are both atmospheric. So that means on both sides they're the same. So I can cancel these two out because they're identical. Next, let's use our energy brain and say, look, why don't we make this y equals 0? So at the hole, there's no potential energy. It's 0. And the energy at the top will be equal to this y distance here. Okay? And then last thing is a little math trick. So we've already established that the velocity coming out the hole is much greater than the velocity at the top. That means the velocity of the water coming downward is small. Okay? And since it's small, then small squared means extra small, and extra small, let's neglect it and say it's approximately 0. So it's about 0. That leaves us with rho gy at the top of the fluid equals 1/2 rho v squared at the hole. And the density is the same, right? And so we get this. So the velocity of the water, if it's water, at the hole must equal 2gy square root, which amazingly enough would be the same as if we took a drop of water at the same height y and dropped it to this point right here. What would its velocity be? Well, it has mgy, potential energy at the top. It has 1/2 mv squared kinetic energy at the bottom. The mass of the drop is the same. And hey, look at that. It's the exact same velocity. Amazing. And so there's our equation. By the way, that's called Torricelli's equation, if you're curious. That's it. All we have now to do is to work through some review problems. So we'll do that later. Bye-bye.